In this work, we present a learning-based approach for translating from natural language commands to linear temporal logic specifications with very limited human labeled training data. Given a list of possible linear temporal logic, or LTL structures, and a list of possible atomic propositions, each associated with natural language description, our goal is to learn a mapping from natural language to LTL, that is, given a natural language command, we wish to translate it to its associated LTL form, which provides an unambiguous task specification for the robot to act upon. Our proposed method leverages various innovations from the low-resource semantic parsing community and can be organized into 3 stages: data synthesis, training, and evaluation. For data synthesis, we aim to obtain LTL and natural language pairs to train the translator. Given the possible LTL structures and atomic propositions, we first enumerate all possible LTL formulas. Then, we convert these LTL formulas back into structured English. Depending on the complexity and quality of the dataset, this can be done either by an LTL to English translator or by a few queries to human experts. Then, by leveraging large language models to paraphrase the structured English, we can synthetically generate a large corpus of diverse English commands. Together with the enumerated LTL formulas, this forms our model's training data. We then use this data to fine-tune a large language model for semantic parsing. Here, we explore 2 variants. First, training the model to output the raw LTL formula, and second, training it to output a canonical form of the LTL formula, which is an intermediate representation between LTL and English. Finally, at evaluation time, we improve translation performance by applying constrained decoding, which enforces that the model's output is syntactically consistent with LTL. We evaluate our translation accuracy on 3 natural language and LTL datasets from the literature and consider 2 data regimes. First, in the regular data regime, we train on these datasets, which consist of thousands of training data pairs. In this case, across all 3 datasets, the 2 variants of our method consistently outperform the baseline methods by around 2% on average. Second, in the low resource regime, we are given at most 1 human annotation per LTL formula, and this corresponds to only around 10 human annotations per dataset, and we must heavily rely on our synthetic data to train our model in this setting. In this case, our method can still provide a competitive accuracy of over 75% on average, while baseline models can only achieve around 43%, and this highlights the effectiveness of our approach. Here, we demonstrate that our method can convert a natural language command into LTL, enabling planning on a 12D quadrilateral model.
Swing by landmark 1 before ending up in the red room.
We summarize our work here. Thanks for your attention.